This is a short video out of 10 for the tutorial that describes setting up the simplest simulation with Lumerical software. I would like to remind you that I provide PowerPoint slides supplemental to this video tutorial. This part discusses setting up the links between the variables and parameters of objects in the simulation domain. It is done by writing short scripts. By the end of the previous video, we have already filled in all variables in the table, and we also specify their types and dimensions. However, right now, these variables are not related to any element in the simulation. We need to create those links between the variables and objects in the simulation domain. We also need links between variables and FDTD parameters. So now we are going to do something different from what we usually do in the CST Suite tool. We need to use these variables as dimension parameters in defining a specific object of the structure. So we need to introduce those links between the variable and the object explicitly. Let me show you how to do it. Similar to the previous case, we select model and then we choose edit object. In this box, we click script and let's consider the first object. We are going to work with this nanoantenna, which is a spherical nanoparticle. Let's start with setting up sphere characteristics. We type select and we identify sphere as an object we are going to define characteristics from. As with any programming language, it's important to follow the syntax. We always need to put a semicolon at the end of each line, otherwise it doesn't work. Then we need to type set. We point out radius as a characteristic of the sphere, and we type the name of the variable that defines that sphere radius. It is SPH radius in our case. This is the link between the variable and the object. In other words, at that moment, we are basically telling the software parameters of the object that will be called sphere. For the parameter radius, the software needs to take the value of the variable SPH radius. Further, we need to define the sphere coordinates. We introduce X origin, Y origin, and Z origin as 0 in the variable list. We can use them now to define sphere positions. We type set X origin, set Y origin, and finally set Z, and we have Z origin plus SPH radius. We click apply to see whether there are any errors, and indeed right now the software tells at line number 2 in the red color. It means something is wrong. There is an error warning because we have not placed that sphere. We have not placed that sphere in the simulation domain yet. So the software gives us a warning that something is wrong with the sphere. But once we introduce the sphere into the domain, this parameter will be automatically taken out from this script. Similarly, I would like to show the procedure of setting up a rectangle. This rectangle corresponds to the homogeneous environment around the sphere and ensures that we have enough space between the sphere and the computational domain boundary. We type select and we identify rectangle as an object we are going to define characteristics for. Further, we need to set up the coordinates of this object. There are 4 parameters that we can use to define object coordinates. It is x, xspan, xmin, and xmax. X corresponds to the coordinate of the rectangle center. Xspan can be regarded as a length in that particular direction. Xmin and xmax are coordinates of 2 edges. We have relations x equal a half of x max plus x min, and x span equal to the difference between x max and x min. They are interdependent, or in other words, related. For any rectangle definition, we need to define any 2 out of 4 in these parameters. For instance, it can be x and x span, or alternatively, it can be x and x min, and so on. This will define the rectangle without ambiguity. The same applies to the y and z coordinates. So for the second object, we want to set up coordinates through the object center and coordinate span. We need to do it one by one for each of 3 coordinates, x, y, and z. So we type similar lines for the x and y spans using variables dx and dy. And for the z direction, we take the range h top plus h bottom. So it is set z span h top plus h bottom, and we set z again. We click apply again just to see the software checking the code. And warning is still there, but it's fine. We click OK. As always, it's important to save the project regularly. And this completes the third video on the numerical simulation with the Lumerical FDTD tool.